So we also have likewise, we also have partial of little r with respect to C1 cross partial of little r with respect to C2 equals the same thing okay, and here I'm going to call this d little a, and all of this is n. Okay, so the question we are asking now is the following: how is little n dA related to capital N dA? How are the area vectors related? Okay? So this is, we are asking ourselves, what is the relation between the area vectors? Okay? In order to do this, we just need to recall, okay, what is the key to doing this? The key to doing this is the following. It is to observe that partial of little r with respect to Ci, I going from 1 to 2, is simply f, the deformation gradient acting on partial of big R with respect to Ci, I equals 1, 2. All right? And so we are then asking, what is the relation between f partial capital R with respect to C1 cross f partial R with respect to C2 and partial R with respect to C1 cross partial R with respect to C2. Okay, this is the question that we've posed for ourselves. To answer this question, we need to invoke a formula that you've probably heard before, right? The answer is what is called Nansen's formula. At least it's called Nansen's formula in the tradition that I'm trained in. Doubtless it's called something else in other traditions. Okay, the answer. The answer is Nansen's formula. Okay. Nansen's formula, we could write it out in terms of f and partial of r with respect to C1 and so on, but just for brevity, I'm going to write it out in a different form, right? And then we'll apply it here. I'm just going to use different labels, really. Okay, so here's how it works. If A and B, actually we're not using A and B, we've previously used U and V, right, as vectors. Let me just go back to those. Okay, if U, V, W and I believe I needed another one. So let me say little s. If all of these are vectors, right, and A is a tensor, right, A has to be such that A is, well, we don't really need this, but let's do it for a special case, okay? Such that A is, actually I don't need it, so let me not do it. Okay, A is just some tensor, okay? All right, Nansen's formula is the following. It says that A U cross A V is determinant of A inverse transpose U cross V. Okay? That's Nansen's formula. We're very quickly going to prove it. Right. You can see now, having defined AU cross AV, how that's applicable to the formula that we are trying to prove at the top of this slide. Right? Okay. So the proof very quickly is the following. Right. Let S be equal to AU cross AV. Okay? All right. Now, write out the following. A transpose S, therefore, is A transpose acting on the cross product of AU with AV. All right? Now, on the left-hand side and right-hand side, we have vectors, right? The left-hand side vector is A transpose S, and on the right-hand side, we have what we've written. Okay, so these are vectors. We're free to dot them with another vector. That's what we're going to do. Okay, so what that implies for us then is that A transpose S, the whole dotted with W, equals A transpose acting on AU cross AV, the whole thing dotted with W. And let me just make clear that it's all of that which is being dotted with W on the right-hand side. Okay? But then, from our manipulation of vectors and tensors and their products involving transposes and so on, written in coordinate notation, we can show that the right-hand side is AU cross AV dotted with AW. Okay? If that seems a little mysterious to you, it's easy enough. Just go back into coordinate notation for the right-hand side and it will follow. All right? Okay, but observe, what do we have on the right-hand side? We have a scalar triple product, which you've studied before in high school or elsewhere. Okay? Now, we have the scalar triple product of three vectors, AU, AV, and AW. Since it's the same tensor A that's multiplying each of the vectors U, V, and W, right, the definition of the scalar triple product can also be extended to tell us that the right-hand side is simply determinant of A times U cross V, the whole dotted with W. Okay? All right. Now, observe that our vectors u, v, s, and w were arbitrary, right? So all of this holds, right? So this result in particular, A transpose S dot W equals the right-hand side, holds for all W belonging to R3, right? But if that is the case, what this implies is that A transpose S equals determinant of A U cross V. Yeah, that's it, right? Okay, but then we see that S equals determinant of A inverse transpose U cross W. Okay, let's see what we started out with. Well, that's what we started out with, right? Look at the statement of our theorem. We have this, and that's what we define to be S, right? The right-hand side is what we proved S to be. Okay, so that does it. All right. Now, applied to our particular result, we have this gives the following, right? F partial R with respect to C1 cross F partial R with respect to C2 equals determinant of F inverse transpose partial of R with respect to C1 cross partial of R with respect to C2. The left-hand side is what we had defined a couple of slides ago as n d little a, okay? And this is what we defined as capital N d capital A, right? So, little n dA and capital N dA are simply the corresponding area vectors, right? So, what we see is that the deformation implies the following mapping of area vectors. Little n dA, the area vector in the current deformed configuration, is determinant of F inverse transpose capital N d capital A. As for curves, so for surfaces, the deformation gradient tells us how they are mapped under the deformation. Okay? All right, we'll stop this segment here.